Is the screen visible? Okay, so today we are going to start a new topic because this is an online class. I'm not analysis you have. So there can be other examples, but that is the most easiest one to understand. So I'll give the example mostly with respect to the sedimentological grain size analysis. So for univariate analysis, we often use the statistics and machine learning toolbox, which is a toolbox built within MATLAB, and it has all the necessary routines. And I checked it all; it is also present in the older versions of MATLAB. Before going into all that, you need to know two important things. So let's say that you have a certain amount of data, and that data can be completely random, or it can have some particular type of distribution. That means some kind of clusterings. So purely from statistical perspective, we classify our data or our samples into two main categories. One is called empirical distribution, which is equivalent to descriptive statistics, and the other one is theoretical distribution. So what is empirical distribution? Empirical distribution is, suppose you have a data and you are analyzing it with some particular ways. That means whatever variation you have is present within the data. Then we call it the distribution an empirical distribution. And if there is an equivalent mathematical theory for it, then that distribution is called theoretical distribution. If this is not clear at this point, I think it will become clear as we go along. So to sum up, whatever data we have, that can be divided into either theoretical distribution or empirical distribution. For empirical distribution, it is the data that we have that is generating some kind of patterns. And for theoretical distribution, it is some predefined patterns that already exist or that has been defined. And then what we do, we often compare between the two. Suppose we have some grain size analysis data of some sandstones, or let's say any sedimentary rocks. So if we plot them by means of statistics, that will be our empirical distribution, which is this one. And if that matches with some predefined theoretical distribution, then we will see that that is matching with some kind of theoretical distribution.
মানে এম্পিরিক্যাল মানে কি মানে এক্সপেরিমেন্ট করে যে ডেটাটা পাওয়া গেছে সেটার
Yes. Suppose you have a set of sandstone data from a particular location. Let's say that you went to Chadipur and you collected samples. Now you are plotting all those data by means of statistics. Let's say the common example would be, let's say that you are plotting the grain size as a histogram. So that will be your empirical distribution. Okay, and there are already prescribed distribution patterns in the literature. Those are called theoretical distributions. So after getting empirical distribution, that is data from after plotting the data our field, we often try to correlate it with our theoretical distribution. And that process is called, in statistics, hypothesis testing. For example, let me give you a simple example. Suppose you have your grain size distribution like this. So this is your empirical distribution. And suppose there is a theoretical distribution that goes like this. So how far these two things match with each other is dealt by the process we call hypothesis testing.
আচ্ছা দাদা, তাহলে তো একটা থিওরিটিক্যাল ডিস্ট্রিবিউশনের জন্য আমার একটা এম্পিরিক্যাল ডিস্ট্রিবিউশন লাগবে, কেননা সেই ডাটাটাকেই তো আমরা থিওরিটিক্যাল ডিস্ট্রিবিউশন ইউজ করছি।
No. Theoretical distribution are purely mathematically derived. It has nothing to do with the amount of data or sample of data.
আচ্ছা,
Okay. I'll come to that. Like once I come to this distribution, this will become much clearer. For example, let's take the example of a dice. If you roll a dice, the probability, or suppose you are trying to plot the probability of getting 1 to 6. That means how many times, or probability of getting 1, probability of getting 2, probability of getting 3, 4, 5, 6. So this can be theoretically derived. So that would be a theoretical distribution for a roll of a dice. Is it clear? That means we can already understand what would be the probability of getting 1 if we roll a dice. How do we know that? Based on some theory. So that would be your theoretical distribution. Now suppose you are getting some sandstone data and you are plotting it in a similar manner, and that can match, or that might match with some other type of distribution, just like I said, like for the roll of the dice. So there are sets of, tens of theoretical distribution that are already present. And what we do in hypothesis testing, we take our sample and we look for which of the theoretical distribution matches with our system or our sample. Okay. For example, here this is a theoretical distribution, right? There is another type of theoretical distribution. For example, roll of a dice. Roll of a dice would be something like this, because let's say this is 1, this is 2, this is 3, so on and so forth, up to 6. And this is probability. So getting 1 on a roll of a dice has an equal probability of getting 2, equal probability of getting 3, 4, so on and so forth. Right? So whatever data we have here does not match well with this data or with this theoretical distribution. But it might match with a different one, which is shown here. I think it is clear now. Okay. So first thing that we are going to talk is the empirical distribution. So here, as I have said, that this is univariate statistics. So here we have only one x-axis, and along, or the data are plotted along the x-axis, Along the y-axis, we actually have the frequency of the data. That means how often we are getting it. And this x represents the number of measurement from a specific object. So the collection of data or sample can be written by this vector, which is equal to x1, x2 up to xn, where n is the number of observations. And the most easiest way of investigating such a data would be by using some kind of graph. And most common type of graph is that we use is histogram. So let us understand what this figure represents. So this represents that along x-axis we have some kind of measurements, and along y-axis we have frequency. So we are seeing that the data, or we have, when the measurement is less than, let's say 8 or 9, we have no data, and the measurement is greater than, let's say 16, we have no data again. So most of the values are falling within the range of, let's say 9 to 16 or 15 point something. And within that, we are seeing that there is a certain pattern of distribution. For example, the maximum value lies here, and then the pattern or the observations are dropping, or the frequency is dropping both along this direction and both along this direction. So there are some ways by which we can measure these things, or we can do some important analysis using from this kind of histogram or this kind of statistical data by means of three things mainly. One is central tendency, the other is dispersion, and the third is the general shape of the distribution. So when we get a graph like this from our data, then we try to look for these three things. One is the central tendency of the data, the other one is the dispersion of the data, and the overall shape of the data. So now the terms that will come, I think you will know all these terms. For example, the measure of central tendency, when we say the measure of central tendency, it basically means three things. That is the mean, median, and mode. So why is it called central tendency? That means whether the data that we have, whether or not they are occurring at the central portion of your observation. That is why they are called the measures of central tendency. So easiest way, or easiest one of or the most common one of the measure of central tendency is the arithmetic mean, which is what? Which is sum of all the data divided by the number of observations. So it means all the data we had is xi, let's say x is the data and I is the number of observations. X is the total number of data and n is the number of observations. So we are dividing our all the data by the number of observations, and that will give us the mean, or the not just the mean, the arithmetic mean. And for most univariate data, arithmetic mean is similar to what we call average. So basically we are averaging it out. Now, the point is the arithmetic mean is very sensitive to something called outliers that I will come to later. What is outlier? Suppose you are seeing in this, let's take the figure A. Try to understand this very carefully because these concepts are very important in geostatistics. So in this figure, we are seeing that let's say for the time being, the mean is at the very center. Because the observations or the frequency of getting an observation is decreasing on both sides, that means mean is at the very center. Now, let's say that you have a particular data which falls here or here. That means our range was from, let's say in this picture, from let's say 11 to 14 point something. Now you have a particular data point that falls far below that, only a single data point. That data point is known as outlier. And the problem with mean is that it is very sensitive to outlier. That means this data should have a mean that is here, because this should be the average of this data at this point. So without the outlier, it is accurately measuring the average of the data. But if you have an outlier, then the mean value will change drastically. That means what? That means although mean is the easiest one, it is not the best measure of central tendency, because it is affected or it is sensitive to something called outlier. Is it clear?
Huh.
Okay. So the next one, which is less sensitive, somewhat less sensitive, is called median. And that is why statistician brought these other terms, like say, let's say, like you have heard this term median and mode and everything. That is because mean is not applicable always. And one of the example that I gave you about outlier, so it is not a good approximation. Mean is not a good approximation of central tendency when you have outlier in your system. So for that we use median. And what is median? Median is the x value that is the middle of the data set. That means 50% of the observation would be on the smaller side and 50% of the observation should be on the larger side. So for figure A, mean and median should be exactly the same, because this picture is almost not almost, this picture is symmetrical. So if we take the exact central point, 50% data would lie on the left and 50% observations would lie on the right. So for this, as long as the outlier is not there, there is no outlier. So for this figure, without the outlier, the mean and median right hand diagram. Now the right hand diagram, the mean would be simply the average of all the data, but here the median is, as you can see, shifted towards the right direction. Why is it shifted towards the right direction? Because as you can see here and here, there is more number of observations. So since the observations are more, or the observations is rather what we call skewed, the median has shifted towards the that direction, because we have more observations here but less observation as we go along this. So like this, from let's say this is 1 to let's say 5. So 1 to 5 we have 50% of the observation, and 6 and 7 contains rest of the 50% of the observations. So median is occurring at the junction between the two. But mean do not consider about the observations or the 50% of the, or half of the observation. It takes the just the average of all the value. That means suppose you have 5 data, then x1 plus x2 plus x3 plus x4 plus x5 by 5. That would be your mean.
আচ্ছা, রাইট সাইডের ডায়াগ্রামটাতে
Hmm.
এক্স এর ভ্যালু 6 যেটা,
Hmm.
সেটা যদি আরো বেড়ে যেত, ওই 40 বা 50 হয়ে যেত, তাহলে মিডিয়ানটা কি হতো?
মিডিয়ানটা আরো ডান দিকে সরে যেত।
কিন্তু মিডিয়ানটা কি ওইটার উপর ডিপেন্ড করছে?
কতগুলো অবজারভেশন তার উপর ডিপেন্ড করছে। মানে median would be the central position on the right of which you will have 50% of the observation, and on the left of which you will have 50% of the observation. Okay.
তো আমরা মিডিয়ানটা কিভাবে ক্যালকুলেট করি? মানে ফার্স্ট অবজারভেশনে 10টা আছে, তারপরের অবজারভেশনে 12টা আছে, এরকম ভাবে যদি কি করে বলবো?
হ্যাঁ, মানে ধর প্রত্যেকটা ধর এখানে ধর এই বারগুলোতে ধর এগুলো তো প্রত্যেকটা অবজারভেশনকে রিপ্রেজেন্ট করছে। ফ্রিকোয়েন্সি মানে তো অবজারভেশন,
হ্যাঁ,
রাইট? তাহলে ও হচ্ছে প্রত্যেকটাতে ক্যালকুলেট করবে। আচ্ছা, তো এই ছবিটা দেখ, ইন দিস পিকচার দিস ইজ সিমেট্রিক্যাল।
হ্যাঁ,
তাহলে ওর কি হবে, এই সেন্ট্রাল পয়েন্টের রেসপেক্টে এদিকে ওর 50% অবজারভেশন থাকবে, এদিকে 15% অবজারভেশন থাকবে,
হ্যাঁ,
রাইট? তাহলে মিডিয়ানটা হবে তার সেন্ট্রাল পয়েন্ট। বাট এখানে এই সবকটা মিলিয়ে যতগুলো অবজারভেশন আছে, অনলি এই দুটো মিলিয়ে ততগুলো অবজারভেশন আছে, তাহলে মিডিয়ান হবে অ্যাট দ্য জাংশন বিটুইন দ্য টু। সাপোজ এখানে যদি আরো থাকতো, তাহলে ইট উড হ্যাভ শিফটেড ইভেন ফার্দার রাইটওয়ার্ড। যেটা বলছিলাম সেটা হচ্ছে যে এটা দেখ, হাউ ডু উই ডিফাইন মিডিয়ান? মিডিয়ান এক্স বার or x tilde equal to x n plus 1 by 2. n টা মানে হচ্ছে number of observation, so we are just dividing where the number of observation is n plus 1 by 2, that means the total number of observation by 2, right? So the location of x where we have n plus 1 by 2. Okay, so suppose you have 50% observation only just here, so your median, the x value corresponds to median would be here. Whether in this case the x value corresponds to median would be at the very central, because both side has 50% observation. So median is defined by based on the observations. Okay, ক্লিয়ার হলো?
হ্যাঁ।
এটা তো 2 দিয়ে ভাগ, ঠিক আছে, এটা
স্যার,
তো 2
একবার।
দিয়ে ভাগ।
আচ্ছা, what is important, although outliers do affect median, it is not as influential as in case of mean. Okay, next term is quantiles. Quantiles is quantiles are a more general way of dividing our data sample. How do we define quantile? We define by equal numbers of observation on each side. So it is a more general way of saying, let's say for median we have 50% on each side. So for quantile we can have n values on each side. For example, the easiest way to understand it is to understand the concept of percentile. What is percentile? Percentile is we divide our data. Suppose you are considering marks in exam, and the marks is based on 100. Let's say for 100 for ease of understanding. Now we define. Let's draw a diagram. So this is our number line. Here we have 0, and here we have 100. Okay. Now we divide it into 99 divisions, and we see how the numbers are distributed. So for that we call it is a percentile, because we are dividing it into, let's say, 99 divisions. Similarly, if we divide it into let's say 4 groups, then we call it quartile. That means the total data we have, let's say we have a total data, we are dividing into 4 groups. That means we have to divide it into 3 times. That will give us 4 groups, that is Q1, Q2, Q3, Q4. Okay. I think এটা বোঝা গেল। suppose the month, like total month হচ্ছে জানুয়ারি থেকে ডিসেম্বর, জানুয়ারি ফেব্রুয়ারি মার্চকে বলে Q1. Why? Because it is within the first quartile. What is quartile? That means totalটাকে হচ্ছে 4 ভাগে ভাগ করে দিল, and the first part is the Q1, the second part would be the Q2, third part would be the Q3, and last part would be the Q4. Similar concept is for percentile. If it divides it into hundreds, 100, that means from 0 to 100. And the general concept of dividing the whole thing is called quantiles. Okay, and কতগুলো ডিভাইড করছি তার উপর ডিপেন্ড করে আমরা কি নাম দেব। 100 হলে হচ্ছে তার পার্সেন্টাইল হবে, 4টে হলে হচ্ছে কোয়ার্টাইল হবে, 5টা হলে কুইন্টাইল হবে, so on and so forth. Okay, I think it is clear. নাকি আবার আর কোনো এক্সাম্পল দিতে হবে, এটা না বুঝতে পেরেছিস? Okay, I hope it is clear. Achha. Last important measure of central tendency is the mode. What is mode? Mode is the most frequent X value. Okay, that means it is simply the value that is occurring the most. So in this figure, this is the one that is occurring the most, so this would be the mode. In here, this is the one that is occurring the most, that would be the mode. Right? For example, in let's say in sedimentology you say unimodal distribution, that means you have one peak value. Okay, similarly we use bimodal distribution or polymodal distribution. So here you can see this is a picture of a bimodal distribution, because there are 2 peaks, one is here and one is here. And for polymodal we will have multiple peaks. For example, in this figure, here, here and here. So this is another way of understanding the central tendency, which is the measure of the most frequent X value. For example, let's say that you have a sandstone with some pebbles and some amounts of mud. So if you plot phi in the x-axis and again frequency on the y-axis, you will get what? You will get a frequency distribution which is like this. So what does that mean? The sand, which is the grain size is the moderate, has the maximum frequency, and here you have pebbles or conglomeratic material, and here you have the like fines that means the silt and clays. So both are low. So how do we know that? Because the mode of the distribution it falls within phi of, let's say, medium sand or something. So that could be a measure of, let's say, central tendency. Achha. We use, do remember this, we use mean, median and mode where several quantities are added together to produce the total value. Okay, for example, where we show the mean value, it is the summation. This is why this symbol is there, because it is the summation of all the values, right? But instead, what if it is the product of all the values? Right, for that case, we use something that is called geometric mean. So for summation, we use, suppose the sum of all value, again the sedimentological example, what constitutes a sandstone? Sandstone is constituted by, let's say, mud plus silt plus sand plus conglomerate. So we are summing them up. That is why mean, median, mode is important. But if, for example, it is being multiplied, then we will no longer use the arithmetic mean or median or mode. For those cases, we use geometric mean. For example, let's take this example. The population of organisms increases by 10% in the first year, 25% in the second year, and 60% in the third year. So by using arithmetic mean, if you average it out, it will give you a wrong average. What you have to do instead? You have to use the formula for geometric mean, which is this. That means you have to multiply each observations and then divide it by the total number of observations that you have made. I think it is clear. So only if the observations are summed up to get a total, then only use arithmetic mean or average and median and mode. If something like organisms, they multiply, or any other example where it is not the sum, then you won't use the normal arithmetic mean or even median and mode. There is another type of mean which is harmonic mean. It is often used if we have a asymmetric data or log normal data. We will come to this later, but do remember this is another type of mean where we take actually the reciprocals of the observations, and it will be in the denominator. Like up to this point, the number of n was always in the denominator, right? Whether it is geometric mean or it is arithmetic mean, the number of observations was in the denominator. So here the number of observation would be at the numerator, and x would be the reciprocal x would be at the denominator. So for harmonic mean, it would be the n by 1 plus x1 plus 1 plus x2 and so on and so forth. And remember that we will use it in if the data is very asymmetric or they are log normally distributed. What is log normal data? I will come to this later. But do remember there are three types of mean then, other than median and mode. there are three means: arithmetic mean, geometric mean, and harmonic mean. Next is the measure of dispersion. So other than Shelton tendency, we can also understand a series or set of data by using how dispersed it is, which is called the measure of dispersion. The easiest or the simplest measure of dispersion is the range, determining the range, which is the difference between max and mean value. For example, here the mean value is, let's say, minus something, and the max value is plus 6. So that would be its range. And again, you probably can guess it by now that they are very susceptible again to outliers. Because suppose you have a data that falls, let's say, here. So your data range would be from 0 to, let's say, 7.5. Although 99.9% data falls within the range of 6. And to overcome this problem, what we do, we often use the interquartile range. That means the middle 50% of the data. That way, what we do, we take where the most, like 50% of the data range, where the most frequent data are occurring, which would be somewhat like this in this figure, and somewhat like this in this figure. So if you consider these as outlier, by considering interquartile data, we can remove these outliers. Interquartile range would always be where the frequency of observations are maximum. So this is one of the way of measuring the dispersion. I think this was somewhat new to you. The other ones are, you have already heard, which is standard deviation. So standard deviation is another measure of dispersion. So again, if we use sedimentology, what is equivalent of standard deviation in grain size analysis? Can anyone tell me without googling it? And you have some sedimentological data, and we do all these things, right, in sedimentology. তোরা পড়েছিস তো?
হ্যাঁ।
So what is equivalent to standard deviation in terms of sedimentological terms, texture and structure? যদি ওটা বলতে পারিস তাহলে স্ট্যান্ডার্ড ডেভিয়েশন বোঝা তো সহজ, তাহলে স্ট্যান্ডার্ড ডেভিয়েশন তো কষ্ট করে বুঝতে হবে না। আচ্ছা, ব্ল্যাঙ্ক। তাহলে আনসার দিয়ে দিই। আনসার ইজ সর্টিং। In terms of sedimentology or textural sedimentological texture, standard deviation is nothing but sorting. So what does it mean in terms of statistics? It means the average deviation of each data point from mean. Okay, so like this is a cumbersome relationship, but look at it into this way: x bar is the mean value. So suppose you have an observation xi, how it is deviating from that mean value? How is it deviating from the mean value? That is squared, and then you have given a root. So it's the same thing only. So whatever your mean value is, how far your each data point is deviating from your mean value. Now if you think of in terms of sedimentology, that is exactly the meaning of sorting. Suppose you have a very well sorted sedimentary rock, so it will contain what? It will contain like a particular grain size of sediment. So that would be your both mean, median and mode. So the variation from that mean value would be very low. So the standard deviation would be very low. I think it is clear. So it is simply you think of in terms of sorting. Right. So let's say this is your grain size analysis curve. There is one rock which is showing like this is phi, and this is frequency. Phi means phi scale of grain size. So here you are seeing that most of the grains are, let's say, sand. But let's take another diagram where it is like this. So that means you have considered amount of both conglomerate and, let's say, silt in your system other than the sand. So you have many data point where the value of xi minus x mean is high. So standard deviation would be significant. Clear? And same goes for variance. Variance is nothing but the square of standard deviation. That means same formula without the root. That is why it is called a square. I think this equation is rather simple if you carefully look at it. So this represents the difference from the mean value, the square of the difference of the mean value. Then you are summing it over for all elements, and then the numerator you have the number of observation minus 1. Why this minus 1? That I will teach later. Why this minus 1 occurs in standard deviation.
আচ্ছা ভ্যারিয়েন্সের সিগনিফিকেন্স কি, মানে জাস্ট স্কোয়ার করে দিচ্ছি কেন?
জাস্ট স্কোয়ার করে দিচ্ছি, আর ওটা জাস্ট কিছু কিছু জায়গা হচ্ছে ওটা ইট ইজ ইজিয়ার টু ডিল উইথ, আর কিছুই না।
আচ্ছা।
আর হচ্ছে সমস্ত ডাটার স্কোয়ার রুট করা যায় না, সেটা একটা প্রবলেম। মানে তুই স্যান্ডস্টোন ডাটার ক্ষেত্রে হচ্ছে তুই উই ডোন্ট ইউজ ভ্যারিয়েন্স, রাইট? উই অলওয়েজ ইউজ স্ট্যান্ডার্ড ডেভিয়েশন। But there are other kind of data, we can have other kind of data where square rooting is not a very good idea. So in those cases we use variance. But that is not a that is not as important as standard deviation. Most cases we use standard deviation. Only if we cannot use standard deviation, then we use variance. Next is, you also know this, skewness. So skewness is the measure of the symmetry of the tail of the distribution, and it is simple, in simple terms it is what? Mean minus mode by standard deviation. So we had in this previous figure, we had a distribution like this. So here, with respect to this central line, let's say that the figure is symmetric, almost symmetric. But now look at these two figures. You can think of this figure as, it is like this, and here it is like this. So as if with respect to this, let's say 1, with respect to figure 1, figure A is skewed towards the right and figure B is skewed towards the left. Right? And for this figure, the value of skewness would be what? 0. So skewness is a measure of how asymmetric your distribution is. So for example, in this case, we have, let's say for grain size analysis, we have much more, let's say silt and clay data, and here we have much more pebble cobble data. A more formal way of defining skewness is by this equation. Okay, and this I have written it because this is how it is defined in MATLAB. Skewness has been defined in MATLAB. So it is basically the difference from the mean, the cube of it, and the cube of standard deviation, the ratio between the two. Last one is kurtosis, which also represents how or what kind of shape your distribution have, and the formula is just same as the other one, just to the power of 4 instead of 3, and it represents how peaked or peakedness of the, or flatness, peakedness or the flatness of the curve. So out of the two, you can see this is more peaked. Like if I draw a curve, it will become like this, but here it would become more flat. What does that mean? That means most of our samples occur within this narrow range. That means it is very pointed, it is very peaked. But here a reasonable amount of samples fall within a long range of this to this.
এটা তো অনেকটা স্ট্যান্ডার্ড ডেভিয়েশনের মতোই মনে হচ্ছে।
Now, standard deviation does not consider the peakedness or the flatness of the system.
মানে এই এখানে লেফট সাইডের ছবিটায় যদি স্ট্যান্ডার্ড ডেভিয়েশন বার করি তাহলে সেটা কম হবে আর ডান দিকেরটায় বেশি হবে।
হ্যাঁ, সেটা হবে। Yes, that is true. বাট এটা তো এরকম হতে পারতো, এই জায়গাটাতে সাপোজ লেটস সে পিকচার সি তে, লাইক ইট উড হ্যাভ বিন জাস্ট আপ টু হিয়ার, দেন ইট উড হ্যাভ বিন নট দ্যাট পিকড। মানে you are getting a particular frequency that is very high, and almost it's like this, and other one is like this.
আচ্ছা, এরকম কোন ফ্রিকোয়েন্সি কার্ভ করা যায় যেখানে দুটো স্ট্যান্ডার্ড ডেভিয়েশন একই কিন্তু কুর্টোসিস আলাদা?
I think it is doable. আমি যখন যখন আমি এক্সাম্পল গুলো দেখাবো তখন আই থিঙ্ক করলে সুবিধা হবে, কারণ এখানে আমার ছবিটা নেই স্ট্যান্ডার্ড ডেভিয়েশনের। Acha. Now let's move on to theoretical distribution. So for theoretical distribution, we need to know or need to remember two important terms. One is probability distribution function. I think you have heard all these terms. And other one is cumulative distribution functions, or this is called PDF, and cumulative distribution function is called CDF. So let's take this set of data. Let's consider the YOLO data. That let's say that we are measuring some kind of sandstone samples and we are getting this kind of data. Now, whenever we get this data, what does that mean? That means, let's say that we have considered grain size of 0.1, 0.2, 0.3, so on and so forth. Let's say. But there can be data that lies within it. So basically what we are doing, whenever we are studying, let's say, sedimentological grain size analysis, we are taking a grain range. Right? For example, let's say that for fine sand it is 1/16 to 1/64, very fine sand. Anything that falls within that range is termed as very fine sand. So by very fine sand, we do not represent a point in the x-axis, right? Rather a range. So it is more like how we discretized our domains in geomathematics. But it's the other, like we have to do it in the other way around. So for geomathematics, we had a continuous function and we discretized it, right? But now the data that we have, that is discretized. Now think that suppose instead of these ranges, we had very small ranges. That means we are subdividing this into very fine parts, and we are considering all the data. Then instead of this kind of irregular pattern, we would have get a continuous curve like this. So that is called our probability distribution density function. So how we call it or how we define it? Suppose we have infinite number of measurements and an infinite small, what we call class width. So if the class width is infinitely small, then instead of an empirical distribution, we will get a probability density function. And this probability density function is defined by fx, small fx. So the probability density function fx defines the probability that the variable has a value that is equal to, let's say, x. That means in this picture, for x equal to something, our fx value is this. So it is giving an idea of what the value should be. For example, if we take x equal to this, let's say this is x2, that is giving me a value of this, and x1 is this. Similarly, let's say x3 is giving us a value of this. So it is more or less mimicking the data that I have. For example, there are some kind of undershooting or overshooting going on. For example, in x1 it is overshooting the data, and in x3 it is undershooting the data. But more or less it can guess to some extent how much data or how much frequent our data is by some theoretical means. So that is called probability distribution function or probability density function. বোঝা গেল? I think simple enough যে তুই একটা হিস্টোগ্রাম নিলি, হিস্টোগ্রামে যদি এই উইডথ গুলোকে তুই যদি ইনফাইনাইটলি স্মল করে দিস আর নাম্বার অফ অবজারভেশন যদি ইনফাইনাইটলি লার্জ করে দিস, then we will get a smooth curve instead of this discretized one, and that will be called probability distribution density function. So if we sum them over, or if we take an integral of it, then it is called cumulative distribution function. So it is the sum of the frequencies of a discrete discrete probability density function, and it is the integral of a continuous density function, probability density function. That means, let's say that, let's again take the example of sedimentology. So suppose you have some small very fine sand, some fine sand, fine medium sand, fine coarse sand, some very coarse sand. So when you are calculating, you are summing over the last one. For example, like you have the density, let's say that this is our coarse sand, this is our medium sand, this is our fine sand, and this is our very fine sand. And the distribution is something like this. Let's say this is x1, x2, x3, x4, x5. So as you are going, or as you are calculating, you are summing this one with this, then you are summing this one with this, then you are summing this one with this, such that the whole becomes normalized to, let's say, 100% or 1. So then we will call it a cumulative distribution function, or cumulative cumulative density function. For example, here you can see what they are doing. Let's say it is starting from, let's say, 8 point something or 9 point something, then it is summing up all the values that occurred before it. So as a whole, you are getting, for example, here it is normalized to 1. So in the end, you are getting this 1. And again, if you want to match it with some theoretical curve, that will be your continuous cumulative distribution function, which is something like this. That means if we have a data whose PDF is like this, then its CDF would be like this. Why? Because look carefully. There is a gentle slope, then there is a steep slope, then again there is a gentle slope. Why is it so? Because initially there is a low amount of data. So that corresponds to this low increase in the CDF. But then there is like many observations in the central region, here up to here. So that corresponds to the sudden increase in the slope in the cumulative distribution curve. And then you have again slowed down or you have less observation, so it is again flattened out. So let me give you an even simpler example. Suppose you have a sedimentary rock that has very few conglomerate and very high sand and very low silt and clay content. So its PDF should look something like this. Let's say this is the phi, this is there. So what does that mean? That means for high grain size and low grain size, you don't have any observation. But for moderate grain size, which is related to, let's say, medium sand to fine sand to coarse sand, you have suddenly, there is a jump in your observations. That means you are getting a lot of sand. So if we draw the cumulative curve for it, so cumulative curve won't increase up to this point, which corresponds to this. Then there will be a sudden increase, and then again there will be a drop, which corresponds to the clay content. That means it was almost flat at the beginning, then there is a sudden slope change, almost vertical, because of the presence of the sand. Then you have again flat slope because there is no mud or sand in silt in the system. So both the CDF and PDF can be interpreted to understand what kind of data or what kind of observations we have just by looking at the curve itself. For example, in this figure, there is a width between this region and this region. That means it is rather flat, like this. Clear? Okay. So let's move on to the different kind of common distributions. One of the common distribution we can think of is the uniform distribution. So what is a uniform distribution? So uniform, or it is also called a rectangular distribution, is a distribution that has constant probability. For example, rolling a dice. On the left hand side you are looking at the right hand picture, you are looking at the example of rolling a dice. So you have 1, 2, 3, 4, 5, 6. They all have equal probability. That means you getting a 1 or 2 or 3 or 4 or 5 or 6 has equal probability. So what would be the value of small fx? Would be 1 by n. That means n is the number of time or number of observations simply. So for our case it would be n is 6, let's say. So for 6 observations, 1, 2, 3, 4, 5, 6 have equal probability, which is 1 by 6. And if we write it in terms of cumulative distribution function, then it will be x into 1 by n. That means it will increase as we along a straight line, as we go from 1 to 6. That means when we are looking at 2, we are also taking the probability of 1 into account. When we are looking at 3, we are also considering the probability of 1 and 2 both into account, so on and so forth. In general, we do what? We do this, we sum the probability, sum up all the probability to become 1. And that is done in this way if it is a discrete function. And if it was a continuous function, then we would have just simply taken integral of minus infinity. So this is done so that the sum of all cumulative functions or CFD becomes 1. You won't get any value beyond that. So this is called uniform distribution, where the chance of getting something is equal. Next is binomial distribution or Bernoulli's distribution. So let me just read it out. A binomial or Bernoulli distribution gives the discrete probability of x successes out of n trials with a probability p of success at any given trial. Okay, let me give you the example. Okay, let me go to the formula first. So formula is fx, or the distribution function's formula is fx is this is basically is ncx. That means n combination x into p to the power x. P is the probability into 1 minus p n minus x. So this seems rather abstract. Let me give you an example. So let's consider this example very carefully. Okay, so let's say that an example for the application of this distribution is to determine the likely outcome of drilling of well. Suppose you are drilling a particular location for oil, and you know the probability of drilling success is 0.1 or 10%. Now suppose you are asked the probability of getting x equal to 3 successful wells out of a total trial of 10. Mane, you have given that the probability of drilling success is 0.1. That means 10%. That means 1 out of 10 or 10 out of 100 on an average means by probability is successful. Now you have been asked that what is the chance that suppose you drill 10 wells, you will get 3 successful drilling, and that can be done by using this formula, which is basically for here the x is 3. That means the success rate should be 3. That means we should get 3 observations. Think of it like this. So n is 10. That means the trial is 10 and the observations should be 3. So it should be 10 combination 3 into the probability, which is 0.1 to the power 3 into 1 minus 0.1 10 to the power 10 minus 3. So that would be 6%. That means what? There is a 6% chance that if you drill there 10 times, you will get 3 successful wells. And this distribution is called binomial or Bernoulli's distribution. And this is shown here in this figure A. So you can see, since the probability or p value is 0.1, so this fx is to some extent related to p value. That means the probability value. So if p is 0.1, then the curve becomes actually like this. Where x is 0, 1, 2, so on and so forth. That means 0 means what? You won't get any well. And 1 is you will get 1 successful drilling. 2 is 2 successful drilling, and so on and so forth. Or anything, for example. But if you see, if the p value is 0.3, then the curve is like this. That means you have higher chance of getting 1 or 2 successful or even 3 successful drillings out of 10. Or rather, I didn't articulate it, I think, properly. The chance of getting 1 successful drilling is rather high, 2 is also high, and 3 is also moderate. Here, for if the probability is low, then in this figure, look at the 3. That is very low, which is basically the 6%. But here it would be around, let's say, greater than 20%. So this distribution is called binomial distribution. এটা বোঝা গেল না গেল না? আমার মনে হয় বোঝা গেল না অনেকের। Okay, do remember that from now on you need to consider this probability thing.
which has been predetermined. For example, for oil drilling, there is a already there is a guessing that the success rate is 0.1 or 10%. Based on that, you are calculating your chance of getting oil. So next is what we call Poisson's distribution. Now I think you have heard this term to some extent. I think you have heard this term, the Poisson distribution. So Poisson's distribution is nothing but a special case of Bernoulli's distribution. How? When the number of trials is very high and the success probability is very low. So this is a extreme case of Bernoulli's distribution where the number of trial is very high and probability of getting one is very low. For example, earthquake or tsunami. So guessing a earthquake and or tsunami is very low. Although we are taking a lots of data, that means n is very high, but probability of understanding or when exactly an earthquake will occur is very low. And for these cases, we can do what? We can simply multiply this number of trials and the probability into a single term, which is lambda. And this generally works for when? If n greater than 100 and p greater than 0.05. For example, let's say earthquake or volcanisms. And for that case, our PDF becomes like this, that is e to the power minus lambda into lambda to the power x by x factorial. And then from that we can get cumulative distribution function like this. So here you can see for lambda equal to very low value, it is actually like exponentially decaying. Here also it is decreasing like this. So you can think of it as an extreme case of Bernoulli's distribution, and this is applied when you have some, let's say, earthquake data, you have, let's say, storm data, tsunami data, volcano data, etc. So this is called Poisson's distribution. Next is normal or Gaussian distribution. So this is also a special case of binomial distribution or Gaussian or Bernoulli's distribution. When p is 0.5, that means it is symmetric and no skew. And you have a 50% probability. That means it is skewed just like this. And under this scenario, along with n is greater than n tends to infinity, the binomial distribution approaches a normal or Gaussian distribution, and this is defined by means of the mean value, and here the notations are different, and the standard deviation value. And the formula for Gaussian distribution is the CFD, the PDF for Gaussian distribution is this. So again, it is not that complex. It is basically, this was the mean. That means this was equivalent to x bar. So it is the difference between x minus x bar by over the standard deviation. And then it is an exponential function of the same. And the curve would look like something like this. So for different standard deviation, we see that although the curve is being flattened, the central region is still symmetric. that means there is no skew in the system in all these cases. And the corresponding cumulative distribution function would look something like this. Like this one. আচ্ছা, একটা কোশ্চেন আছে, সেটা হচ্ছে লুক এট দ্য কিউমুলেটিভ ডিস্ট্রিবিউশন ফাংশন। কোন কার্ভের সঙ্গে মিল পাচ্ছিস যেটা জিওডাইনামিক্সে পড়েছিলাম?
হাফ স্পেস কুলিং।
একটা পার্টিকুলার কার্ভ ছিল যার সঙ্গে এটা ম্যাচ আছে এক্স্যাক্টলি আর কি, এই আমি যেটা ড্র করলাম, ইট ইজ রিলেটেড টু হাফ স্পেস কুলিং। হ্যাঁ, কিসের বলতো? এইটার।
ও হ্যাঁ হ্যাঁ হ্যাঁ,
যদি এরার ফাংশনকে দেখিস এক্স্যাক্টলি হচ্ছে একটা ছিল এরকম, একটা ছিল হচ্ছে
মানে একটু উল্টো দিকে। হ্যাঁ,
so like যেটা এদিকে ছিল that is exactly looks like this. And if you like when I was talking about the like thermal structure of plutons and all, ওখানে দেখবি যে temperature variation টা exactly follows a cumulative distribution function of Gaussian distribution. আচ্ছা, a variation of Gaussian distribution that we most commonly use is called standard normal distribution. When do we use it? Like it is a special member of normal distribution family that has a mean of 0 and standard deviation of 1. So if standard deviation is 1 and mean is 0, so instead of writing all this, we just write this as z. And the whole formula becomes this. I think this is very simple to easy to remember. You have to remember at least this one. That is 1 by root 2 pi exponential minus z square by 2. And because we consider this z like this, we call it z distribution. So it is just the function of, it is now just the function of z, because standard deviation is 1 and mean is 0. That means here if you look at this part, so this becomes 1, so it is just 2 pi part, and here also it becomes much more simplified because the mu is or x bar equal to 0. So that is called standard normal distribution or z distribution. Lastly, we have a log normal distribution, or what is the logarithmic normal distribution. So that is very similar to normal distribution, except for that it is skewed. It is skewed towards this side. So how is it different? It is different just by this. Instead of x, we have log x or ln x rather. So this kind of distributions are called log normal distribution. So the last 4 or 5 distributions that I have talked are all theoretical distributions. So whenever you have a data, you would see that your data would match with, and there are other theoretical distributions also, we try to match our data with one of these data. For example, let's say whether or not we have data that looks like this or data that looks like this, so on and so forth. And also, like we know when to use which one. For example, as I have told you that like let's say that Poisson's distribution will be used when like the probability is very low, like less than 0.05. That means suppose you want to work with flood related data or earthquake related data, then you probably your data will be closely matched with a Poisson distribution. কোনো ডাউট আছে তাহলে বল। আরেকটা জিনিস দেখাবো, কয়েকটা জিনিস ম্যাটল্যাবে খুবই সিম্পল জিনিস, সেই জন্য আমি আর তোদের পাঠাইনি এগুলো। Acha. I hope you can see. So what I am going to do, I am going to take some univariate data. What kind of data? Let's say this is my data. So this is the, let's say, organic matter content in a coal. So as you can see, unlike the data that I have given in the previous class or classes, it has only one column. That means it is a column matrix. Instead of having two data, we have only one data, and the grain size analysis data would be exactly similar, where we will have the concentration of different grains. But there can be other things also which falls under this univariate data class. So let me first load the data, and I'm going to just plot the, let's say, that range of the data. So I hope you can see. Okay. So here the range of the data, not the data itself. So you can see in the x-axis we have the range from 9 to 15. So that is more or less the upper and lower range of the given data. Now I am evaluating the max and min value of the data, and it will give me a value of 14.5 and 9.4. That means the minimum value is 9.4 and maximum value is 14.5. That can be done simply by using this max and min command that like we have already learned. Now let's plot this thing. So I think you can appreciate if we simply plot this thing, like along x-axis we have observations. So we have a total number of 60 observations. So these data are actually very haphazard. And along the y-axis we have these values, for example 9 to 15. So this data in this form, if you simply plot like we have done up to this point, so this data is very haphazard, and there is no distribution in this data, right?
Zeros মানে কি?
আচ্ছা, লাইন 12 এ
হ্যাঁ,
আচ্ছা ওটা আমি ইন্টেনশনালি করেছি so that I can I didn't want to see these fluctuations. Like আমি কি করছিলাম যে রেঞ্জটা জাস্ট দেখছিলাম। তো zeros মানে হচ্ছে you are creating a matrix of zeros. আমি আবার ওটা চালাচ্ছি। মানে বেসিক্যালি হচ্ছে ওর ম্যাগনিটিউডটা নিচ্ছে না, সব জায়গায় জিরো করে দিচ্ছে। ওয়াই অ্যাক্সিস বরাবর আমার হচ্ছে কোনো ম্যাগনিটিউডটা দেখছি না, অনলি জিরো।
ও আচ্ছা।
ওটা জাস্ট দেখার জন্য যে আমার রেঞ্জটা কতটা। আচ্ছা, সো this data is haphazard, or like there is nothing informative from this data apart from that it is varying from like 9 point something from this point to let's say 14 point something in this point. But if instead if we use histogram, then the same data would become much more readable. So simply use in MATLAB to draw histogram, just use this আমি এটা পাঠিয়ে দেবো, just use this syntax histogram, then within bracket the name of the data. Like for example here our variable, we have loaded our variable as CORG. So here I would write age, or simply you don't have to write age, histogram, then within parenthesis you will write CORG, and that will generate a histogram data. But what is more interesting is if we look at, so here we have defined this histogram CORG as age. So if we simply write age, it will give us all the like nitty-gritty details that it has. For example, this data is a 60 by 1 double. That means it has 60 rows and 1 column. That means it is a column vector. Then let's look at bin width. Okay, so this each individual part is called a single bin. Okay, that means how many bins we have? 1, 2, 3, 4, 5, 6. Right? You understand what is a bin? Or the bins are the individual these columns. So we didn't define how
রেঞ্জ গুলো কোথায় ডিফাইন করলাম?
we didn't. That is the point. We didn't define the bins. What MATLAB did, MATLAB analyzed the data and it defined the bins automatically. MATLAB can do all these things. Okay, so it defined the bins for you and it is giving you the properties of that bin. For example, it is saying that it has constrained the bin limits to 9 and 15 under this notation bin limits. Then it is saying that I have taken bin edges as 9, 10, 11, 12, 13, 14, 15. That means each bin width is 1. MATLAB itself has taken each bin width as 1. That means 9 to 10, 10 to 11, 11 to 12. That means we have seen the max and min value was 9 point something and 14 point something. So MATLAB realized that there is no data outside this range, that is 9 and 15. So it then divided the range, that is or limit 9 to 15 into bins of width 1. That is why you can see the bin age is 9, 10, 11, 12, 13, 14, 15 and num bins means number of bins, which is 6 because we have 6 bins. What else is there? You also have one thing that is called values. That means how many data you have within each bin. So from 9 to 10 we have 2 data, from 10 to 11 we have 6 data, 11 to 12 we have 13 data, 12 to 13 we have 20 data, 13 to 14 we have 15 data, 14 to 15 we have 4 data. I think it is clear. So it is already generating all these things for you. You don't have to do anything, but you can manipulate it if you want. So what I have done next, okay, let's forget about these two parts. So if you want to, let's say for example, if you want to get these values, right? What you do, you have defined H as the histogram. Then suppose you want to get the values, so you give another variable, which is, let's say here it is n, and that is equal to H then dot. You have to give a dot operation. You have to do a dot operation. So if you write H dot values, then it will give you the values of H. That means these things. And this is not just for histogram. Any MATLAB program can do these things. So if I
শুধু get h করলেই পেয়ে যাবো।
Now we are just extracting the values. মানে each বিনে কতগুলো ভ্যালু আছে, we are just extracting that part, and we want to see it. Suppose, so if we write n, it will give us these values. That means in the first bin we have 2 values, in the second bin we have 6 values, in the third bin we have 13 values, so on and so forth.
ভ্যালুসটা কি একটা ফাংশন?
Yeah, it is not a function. It is within the histogram. Whenever you are drawing a histogram, MATLAB is creating all these variables for you within that histogram itself. So you are defining a variable that contains all the variable of histogram by calling it as H. So when you write H dot values, MATLAB knows you are asking for these values from the H. These values from the H. So you are asking for this matrix. So what are the frequencies of each bins within each bins? Similarly, in the line 36, I'm not going to explain that. What I have done here, I have defined another function that would give us the central point of each bin. That means if we look at the figure, what is the central point of each bin? That means here it is 9.5, here it is 10.5, 11.5. I have done it using this line of code. So if you are interested, you can look it up, but it's up to you. Okay, let's move on. So if you want to determine the mean, you just write mean within parentheses your name of the variable. So here the mean value is 12.3448. Similarly, if you want to calculate median, you simply write median within parentheses the name of the variable. And for our case, the mean value is 12.3448 and median value is 12.4712. That means they are actually very close. So it is very close to a what we call, like, let's say that it is closer to a normal distribution because the mean and median value are very close. I think these are easy, very easy. Like, you don't have to learn much of MATLAB to understand this. Like, simply the comment mean, then your variable name within parentheses, it will give you the mean. Similarly, the median within parentheses, it will give you the value of the median. Okay. Let's skip this one. Finding mean is rather tough.
So how do we find mean? How do we define? Sorry, not mean. Mode. How do we define mode? Mode is the maximum value of x, right? So here we have defined n as n values, h the values of h. So we ask MATLAB to find the maximum values within n by writing n equal to double equal to max of n. That means what is the max value within n? And that would give us the mode of the problem, which is 12.5. So for our problem, mean, median and mode, all three are very close to each other. Right? Which can be seen from this figure. So here we see, although there are two beans on the right hand side, but the measurements of bean on the right hand side are more than that of in the left hand side, than the central bean. That is why both mean, median and mode are falling near to this region, right, within this top of this central bean. Now let's learn how to code quartile. So simply to understand quartile, we will use the function quartile, and suppose here we want to divide it into 3 or 4 divisions. So we are giving quartile, then within parenthesis quart, then comma, then within we have to create a matrix that contains 0.25, 0.5 and 0.75. And that should give us these values: 11 point something, 12 point something and 13 point something. What does that mean? That means 25% of the data are on the one side of the 11.4054. Okay, a quantile বোঝা গেল. Quantile I mean to say is that, like, you are dividing the whole domain into 4 quartiles. So এই যে প্রথম যে ভ্যালুটা এলো 11.4054, 25% of the data values are lower than this value, and between 11.4054 and 12.4712 you have another 25% data. Then within 12.4712 and 13.2965 you have another 25% of the data, and if you go beyond that you have the rest 25% of the data. Okay. Achha. Next, let's see what is the range. It is simply by using the command range. So it gives the maximum minus the minimum value. So for our case it is 5.4147. Similarly, the standard deviation and variance, or the standard deviation is done by the command std, and for our case it is 1.16. So the syntax for standard deviation and variance is std and var respectively, and here would be the square of standard deviation. And for skewness and kurtosis, the skewness formula of skewness would be SKUW in intervals, just like their whole terms as it is. So here the value of skewness is negative. Why it is negative? Because as you can see in this figure, it is slightly skewed towards the right. If something is skewed towards the right, then it gives a negative skewness. So simply by looking at skewness, you can say that this is slightly skewed towards the right. Okay, I think it is clear. So next, we will use the same techniques for a data that is more skewed. So here you can see this data is more skewed towards the right. So do notice one thing, that here it is not just the file name after histogram, but also there is a number. So this number simply represents the number of beans. So you can define the number of beans within histogram itself. Let's say that if we do it 20, then it will further subdivide the data into 20 bins. Now let's look at the mean, median and mode and skewness data of this particular graph. So again, the last one is the skewness, which is minus 1.10. Then again, you can see that this is skewed towards the right. That means its tail is towards the left. That is why it is negative. But what you can see, because this data is skewed, the first one is mean, then second one is median, and third one is mode. Mean is 5.66, median is 5.97, and mode is 6.36. That means there is a measurable difference between mean, median and mode. So to conclude that, like if the data is not skewed, then or rather the standard deviation is rather low and it follows a Gaussian-like curvature or distribution, then we will get mean, median and mode value closer to each other. But if the data is skewed, then the mean value would deviate from median and mode. Finally, as I was saying about the outliers, suppose we have a data that contains outlier in it. So up to this point, you can see that here in this case the data range is let's say 13 to 18. The data range is 13 to 18 and most of the data are skewed towards the right hand side. Now I am going to introduce a particular element which is equal to 7. So this should make it skewed. Yes. So there is one data that is the outlier. Now, if we consider the mean and the median and the mode, let's take all the three.
you can see that the mean value is 16.44, the median value is 16.97, and the mode value is 17.45. Whereas if we have taken, actually I should have done this. Let's consider this first. Okay, for this value, the mean value is 16.63, the median value is 16.97, and the mode value is 17.75. But as now you can see, the mean value has been shifted to some extent as compared to the median and the mode value. That means because of the outlier, the mean value is shifted towards the outlier. That means the outlier affects the mean value of the system, and it is affecting the median and mode value much less as compared to the mean value. So you know, when we measure central tendency, that is why measuring the median and mode is as much important, if not more, than simply measuring the mean value. Okay, বোঝা গেল তাহলে আউটলায়ার কি এবং আউটলায়ার হাউ আউটলায়ার অ্যাফেক্টস ডেটা। Lastly, if you want to plot a cumulative density function, then you have to write CDF plot, then your given function. It give me an error because here. So this gave us the cumulative distribution function, but because our data are discrete, not continuous, so the cumulative the CDF is showing this step-like function. Lastly, if you want to learn more, or if you want to see how different theoretical distributions look like, you can simply type DIST tool in the command window and press enter, and that will give you this pop-up. And from here, if you look at the distribution, you can generate, these are all the theoretical distributions that we have. For example, our binomial distribution, or our log normal distribution, or we are seeing the CDF. We can also see the PDF, and you can change the different data to see how data are being changed. For example, let's take normal distribution, which is exactly at the center. Okay, so এটা নোট করে দেন, এটার নাম হচ্ছে DIST tool, TWL. আচ্ছা, আমি স্লাইড এবং হচ্ছে যে ম্যাটল্যাব কোড দুটোই পাঠিয়ে দেবো, সো দ্যাট ইউ ক্যান প্র্যাকটিস। তো কোনো কোশ্চেন থাকলে বল। আই থিঙ্ক এখানে যে ম্যাটল্যাবের যে পার্টটা করেছি দ্যাট ওয়াজ ভেরি সিম্পল, সব এভরিথিং ওয়াজ স্ট্রেট ফরওয়ার্ড, জাস্ট তোকে নামগুলো লিখতে হবে এবং ম্যাটল্যাবই সব করে দিচ্ছে তোর জন্য, বাট পরীক্ষার জন্য তোকে ফর্মুলাগুলো মুখস্থ রাখতে হবে। বলো, কারো কোনো কোশ্চেন থাকলে বলো।